Hi everyone, welcome to IKEAKAR 2020. I'm Adeline Chan, a junior at Union County Magnet High School.
I'm Kevin Yang, also a junior at Magnet.
And I'm Benjamin Jairus, a junior at Magnet High School. And together, we
we're
are the
we are
IKEAKAR
the
team.
IKEAKAR team.
Thank you to Transoptions for sponsoring the IKEAKAR 2020 challenge despite the restrictions posed by COVID-19.
We had a lot of fun collaborating over Zoom, talking about our car design, video improvements, and research, learning all the while.
Without further ado, we present the IKEAKAR. Sit back, relax, and get ready to learn.
Okay, hello, Internet.
Hello. All right. So today is November 6th, 2020, and this is our first meeting, and we're setting a timeline and goals and making sure that we are on track to finishing our car.
Sounds good.
Okay, so this was our initial design, and this was from early on. We started with a horizontal design, and basically the fuel cells would be slotted in, the motor would be slotted in. You want to hold the fuel cell like this, there would be another one over here, and the motor would be over here. And then this was where we would consider putting our syringes. And overall, obviously, we would need a lot of material to hold things together. So we ended up going with something else.
Hi guys, today is our second meeting, November 8th, 2020. And this meeting we're going to discuss our brainstorming that we completed and some possible designs. And we're going to decide on the one that we want to use for our prototype.
So to start, we're designing just one side of the two panels, and here you can see how the fuel cells would slot in. So instead of adding material to a horizontal base, we're taking out material to make room to slot the fuel cells and motors inside. We also have room for the syringes later on. Okay, now we can see the two panels. One has been mirrored, and we also mirrored it so that the space between is accurate to how it would look after the fuel cells have been slotted in. So we had to take some measurements and measurements of the motor, of the fuel cells, syringes, so that we could CAD it properly. There's also an extra bar here for support for the fuel cells, and we will CAD the syringe holders next. Here we've CADed bearing holes as well as our syringe holders. So here you can see that we've chosen to use 5 milliliter syringes, and that's because they're small and enough hydrogen and oxygen gas for what we need. In the past, we've used larger syringes, and that can be troublesome because you need a longer rubber band, and that could always slip and cause problems. And the smaller 5 milliliter syringe also fit perfectly in our design and with our thin vertical chassis.
To store the gases produced during electrolysis, we used 3 syringes, 2 for hydrogen and 1 for oxygen. We decided to use one syringe that would store oxygen gas collected from both fuel cells so that the syringes would all fill at the same rate. This works because the amount of hydrogen gas produced by one fuel cell is double the amount of oxygen gas produced.
Okay, so this is what we call chassis version 1. This was the first chassis that we 3D printed, and basically we primarily used it to test how it looks, get a feel for the actual size of it, and test the tolerances for all of these motors, syringes, and fuel cells. So we can, and as well as the bearing holes. So we can see that there's this curve here. It makes it smoother. Aerodynamics don't really matter here as it's not going that fast, but it makes it look cooler and sleeker. And then we also wanted to test how we would hold together the syringes. So we'll have these ledges here that would hold in the flanges of the syringes. We also have the slot here so that we could interact with the front here and be able to put on the rubber bands on the syringes. So we have a latch here and a latch here, and here is completely flat, so it can go in at a diagonal this way. It can go in this way, and then we turn it to the opposite diagonal. So based on the 3D print for this, we ended up finding that the fuel cells fit pretty well, but the syringes were a bit loose.
How the fuel cells work. One function of the fuel cell is to perform electrolysis, where an electrolytic cell uses electricity to perform an otherwise non-spontaneous chemical reaction. In this case, the electrical energy comes from the battery, and the chemical reaction is a splitting of water into its component gases. Electrolysis is initiated after distilled water is added to the positive side of the fuel cell. The battery produces a potential difference, which results in a negative and positive plate. These plates are the sites of redox reactions. In electrolysis, hydrogen is reduced and produced at the cathode, the negative plate, and oxygen is oxidized and produced at the anode, the positive plate. Now let's take a look at the half reactions that make up electrolysis. At the cathode, electrons are added to water to produce hydrogen gas, and at the anode, electrons are stripped from water to produce oxygen gas. After combining the two half reactions, the final equation tells us that for every 2 moles of water we input, we will get out 2 moles of hydrogen gas and 1 mole of oxygen gas. The amount of moles of hydrogen gas and oxygen gas tell us that the amount of hydrogen gas produced will be double that of oxygen gas. Now let's talk about how a fuel cell converts chemical energy into electrical energy. There's an influx of hydrogen gas coming in from the anode, which is split by the catalyst into 2 protons and 2 electrons. The protons pass through the proton exchange membrane, but the electrons are forced to take an external path. This external path goes through a wire and passes through the motor, which is a resistor. This produces electricity. Then the electrons will meet the protons and the oxygen gas, which enters through the cathode, to form water at the cathode. If you are just considering the fuel cell process and not the process to obtain hydrogen before that, then water vapor is the only waste product. I will talk more about the consequences of the production of hydrogen when discussing fuel cell sustainability in the upcoming slides. The scope of hydrogen fuel cells reach far beyond vehicles. Smaller cells can power small electronics, while larger cells can be used as emergency power sources or sources of energy in areas that are not connected to electric power grids. Wait, Adeline, so is the thing hollow, like partially hollow on the inside?
Yeah.
Okay.
Yeah, it is. There's only probably, it's already thin, but there are probably only a few layers at the top and bottom, and it can print an infill. So this is 10% or 15% infill, and you can have different patterns like a grid inside or hexagons or lines and stuff like that.
It's called infill?
Yeah. And
so how heavy it is, essentially? How much they...
how much they filled up. Instead, 100% would take way longer to make, and it would be a lot sturdier and a lot heavier. So this is by having a lower percentage infill, and then choosing to have a certain pattern like a grid over some maybe other weaker pattern, you're making it both stronger and lighter, and also not wasting material. Okay, now here we start thinking about spacers, because between the chassis and the wheel that's attached to the axle that goes through the chassis, we have to have a space. So we wanted to have a spacer that can not only go in from one end of the axle, but on top of the axle. And then we also had to think about the wheels. We wanted to 3D print our wheels, and we also wanted to 3D print them to fit the hexagonal axles that we would use.
Hi guys, today is November 16th, 2020, and this is our 6th meeting. We just printed out our first prototype today, and we'll be discussing some modifications and maybe some things that we want to add to it.
Okay, so then we had to start thinking about the motor. So we wanted to have a motor mount that would fit inside that square slot we saw earlier in our chassis, and this is how it was supposed to look like. And you would put it in this way, and the shaft would stick out this way. And then the ends where you connect wiring to would be on this side. And here's how it would slot in. And then we printed this one as well.
Now I will discuss the gear ratios of the pulleys. If the gear ratio is big, like in this image here, then you will have less speed but greater torque. Inversely, if you have a small gear ratio, you will have greater speed but less torque. However, the gear ratio cannot be too small, or the torque produced won't be enough to rotate the axle. This is especially important considering the fuel cells don't produce much power.
We chose to have pulleys because we can kind of change the pulley sizes, and we don't have to have a set ratio. So in case one ratio doesn't work, then we could try another one. Because for gears, you need to have them mesh a certain way and them have fixed positions, and you can't really change them without changing the whole design of the car. And we also added these nubs or hooks for the rubber bands, and we also have a nice fillet here that kind of helps us differentiate the outside from the inside. And we also have these squares for our spacers. We discussed that we also wanted to have some clamp out the top to help keep things sturdy and stabilized. So this is the clamp, and it goes on top. The chassis would go through here. The clamp would go right here. And then we also found that the motor, it was only hanging inside by this top flap. So we added something for the bottom, and that would help it to hold together the chassis with the right width and not swing back and forth, pivoting here. Also, we continued to adjust the wheel axles and adjusting for the size to test how the hexagonal axle would be put in. We also made the spacers smaller. As you can see, it was too big earlier, and those spacers would fit right here.
Welcome to our 7th meeting, and today we're going to be discussing the second iteration of our chassis prototype. We're going to be revising the syringe locking mechanism, and we're going to be analyzing the grill clamp and overall looking into the bearings and how they're going to slot in to the chassis. And so far we've revised the motor housing so that it snaps in on top and bottom and locks in. And the chassis is really coming together, and we should have a final prototype next meeting.
So we decided that the fuel cells would be connected in parallel when charging to optimize speed. There are two paths for the current to flow, so the fuel cells have two connections, positive to positive and negative to negative. The negative and positive ends of the battery are also connected to the negative and positive ends of one fuel cell so that the circuit is complete. We decided that we would connect the two fuel cells in series when running the car to maximize power output. There would be one connection between the two fuel cells, which would be negative to positive. And there would also be connection between the positive and negative ends of the motor and the positive and negative ends of a fuel cell. Sustainability of fuel cells and low carbon energy. At first glance, it may seem like fuel cells are completely clean because the only waste product is water. However, in our process, we needed to perform electrolysis first to obtain the hydrogen gas. That process requires energy and we use a battery. But wouldn't solar power be more sustainable because the sun's energy never runs out? Well, not necessarily. And that's because mining for critical materials such as silicon to make the solar panel takes a large toll on the environment. Solar panels can also be toxic to the environment if not disposed of properly. Although we used electrolysis to obtain the hydrogen gas, natural gas reforming is used much more frequently in industry. This process, however, is not environmentally sustainable because it produces carbon monoxide and carbon dioxide. This casts doubt on the sustainability of hydrogen fuel cells as a whole because the most common method of obtaining hydrogen is harmful to the environment. Another aspect of sustainability to consider is the economic side. When considering cars, hydrogen-powered vehicles are not sustainable yet, as shown by the lack of them on the market. This is mainly because they are expensive and inefficient. Currently, they are being outcompeted by electric cars. This is because electric cars use the energy stored in the battery directly, whereas hydrogen cars need to combine hydrogen and oxygen to create electricity, sacrificing efficiency. The industry is promising, however, if companies can find ways to improve fuel cell efficiency, their prices would become competitive with those of electric cars.
So at this point in the video, the observant have picked out the dominant design language that informed the construction of this hydrocar, that of modularity at every turn, even to the point of full disassembly, with mass-producible mechanical 3D printed parts, and iterative innovation with every new version of the IKEAKAR. Furthermore, the worldly among you are familiar with a certain Swedish department store, which flouts the same colors and touts the same engineering ideals. Now the joy of self-assembly is genius. Not only are prepackaged parts more economically and environmentally friendly, but research demonstrates that when we put effort into assembling our own technology, be it a table or a chassis, we develop an emotional attachment to our item, which pre-assembled parts simply cannot emulate. So it is this do-it-yourself passion which lies at the heart of our team and which informed every design decision we have thus presented. So with this car design, we really tried something a little risky. The vertical design, it might be a little unstable, especially with that gap in the middle. So we catted the car with our only thought being modularity at the core of everything we made. So our design philosophy brought out certain rules which we followed as a matter of principle, such as never supergluing to permanize features, instead using locking or slotting mechanisms as witnessed in the motor housing or the clip on the top of the car. We further captured the ideals which we valued in this foreign company through our color choice of PLA material, the IKEA blue, and the nameplates with the IKEA yellow. And of course, the mascot on the two sides of the car, the IKEA man. So it goes without saying that we learned a ton through this group experience. By iterating through each version, meeting by meeting, we found new issues turn up again and again, but over time, their scope began to diminish until we were looking at pedaling issues which didn't reflect a major design flaw in our car. But one problem which did recur was the stability. As discussed, the vertical design is a bit top-heavy. Now because the chassis was thin width-wise, the wheels on the longer axle were a bit farther away to be properly supported. So the axles wobbled due to the wheels being able to pivot on the thin chassis point like a lever. So we added some strengthening screws and a spacer to prevent the chassis from sliding, but the axle was still flexible. Because of this, the rubber band of the pulley pulled the axle towards the motor just slightly, causing the car to swerve a little bit to the right. Now our guide wire, when taut, helped to mitigate this issue, but in the future we would make sure that the wheels were closer to the chassis to prevent this wobbling, and maybe even have a wishbone or triangular structure, similar to that found in real cars, to ground the wheels with the body of the car. Finally, our guide wire eye hooks are slightly offset, and we'd like to see those centered right down on the spacers on the screws. And this might have encouraged the car to swerve a little less, being less lopsided.
Sustainability and the fuel cell in the real world. Let's discuss the advantages of low carbon. First, I would like to call a distinction between water vapor and carbon dioxide. Although they are both greenhouse gases and contribute to global warming, an increase in carbon dioxide can actually exacerbate the water vapor problem, which is why reducing carbon dioxide emissions should be our main focus. Carbon dioxide exacerbates global warming through feedback mechanisms, specifically positive feedback loops, where small change causes many other changes. For example, let's take a look at the water loop. With an increase in carbon dioxide emissions, the atmosphere will absorb more heat and the temperature will increase. The problem is that clouds can hold exponentially more water vapor as temperature increases, as modeled by the Clausius-Clapeyron equation. So, an increase in carbon dioxide emissions causes an increase in water vapor, further driving up the temperature. Another feedback loop describes the ice caps melting in the Arctic. If there's an increase in carbon dioxide, the temperature will increase. Then some of the white ice will melt, exposing the darker water. Then, because the darker water has a lower albedo than the white ice, the temperature will continue to increase, melting even more ice along the way. The carbon dioxide emitted also stays in the atmosphere for hundreds of years, which makes lowering emissions all the more important. Another consequence of increased carbon dioxide is ocean acidification. As shown in the equations, an increase in carbon dioxide causes an increase in protons, or hydrogen ions, which is the definition of acidification. The issue is that many marine organisms, such as coral, have calcium carbonate shells. Because protons also bind to carbonate ions, there's more competition for the carbonate ion, which leads to weakened or even deformed shells, as shown in this image. If we want a greener future, zero carbon will not be enough. We also need to look into negative carbon techniques. One way is converting waste to hydrogen without burning the waste. Another idea is carbon capture and storage, which takes carbon dioxide from the atmosphere and traps it deep underground. Planting trees, of course, which take in carbon dioxide and release oxygen, is also another way to decrease carbon dioxide in the atmosphere. The problem right now is not the warming of the Earth, however. That happens naturally. The concern is the rates that the temperature is rising due to the activities of man. Previously, this same change in temperature occurred, but over millions of years. Now it is happening over decades or even years. Of course, we still need energy, which currently comes mostly from the burning of fossil fuels. That is why the development of new sustainable energy sources and clean energy sources have become more and more important. We hope that by educating ourselves on these matters and experimenting with hydrogen technology, we'll have the ability to contribute to the mitigation of this issue in society in the near future. Finally, these are the resources we use to guide our research.
We could. Have you ever been to IKEA and eaten those Swedish meatballs?
Yeah,
They're
I have.
famous. What if we put a giant Swedish meatball like at the back plate?